Invite Professor Satyajit Das to have a session on Introduction to Artificial Intelligence on Edge. Currently, he is working as a faculty in the Department of Computer Science and Engineering, IIT Palakkad. He has received his joint PhD from University of South Brittany, France and University of Bologna, Italy. Prior to joining IIT Palakkad, he was a postdoctoral fellow at Labstick UBS. His research areas include architecture, methods, and tools for embedded systems, including CGRAs, custom processors, multi-core, high-level synthesis, and compilers. He acted as the session chair for IEEE International Workshop on Signal Processing System and International Conference on Acoustic Speech and Signal Processing in 2020. He was the organizer of CREDS Inaugural Symposium 2020 in IIT Palakkad. Now, on behalf of Power and Energy Group NIT Calicut, I may request Professor Satyajit sir to carry over the session. Over to you, sir.
Thank you for the kind introduction, and it's really a great pleasure to be here today and talking about AI on Edge in this prestigious FDP program. And I'd like to also thank Dr. Deepak for the invitation to speak for 2 days in this FDP. And I look forward to a very interactive and very good session in these two sessions we'll have with you. Okay, with this, we'll just share my screen to start the PPT. Okay, so I hope everybody can see my screen, right?
Yes, sir. Yes, sir.
Okay, thank you, Doctor. Okay, so just in addition to that, what Ms. Meera was speaking about me, but I'd like to speak before starting to introduce my group and my collaborators and my lab also. So here at IIT Palakkad, we are working at LABA, Lab for Advanced VLSI and Architecture. And I'm also associated with Center for Research and Education in Data Science, CREDS, which was mentioned. And in these two labs and the center, we are actually collaborating with Dr. Vivek, Brinal, and Saheli. And for our international collaborations, we have collaboration with the University of South Brittany, France, specifically with Professor Philippe Cusi and Dr. Kevin Martin, and also with the University of Bologna, Italy, with Professor Luca Benini and Dr. Davide Rossi. Currently, these PhD students are working with us. Ms. Chilankamul is a PhD student at IIT Palakkad, and Mr. Sain also is working at IIT Palakkad. And Mr. Rohit Prasad is a joint PhD student at the University of South Brittany and University of Bologna. And Ms. Anju is working also as joint PhD in IIT Palakkad and EBS. So with this, I'd like to start our goal for today is the AI on Edge. As we all know that in today's scenario, one of the big paradigms is of course AI, and there are multiple reasons for using AI in various things as well. And throughout these FDP sessions, you are seeing how AI can be used in several aspects of, be it rather in power electronics, and any other uh, aspects of our modern day lives. But so I'll just give an overview of why first that we are talking about AI on edge, and then we will move forward how to actually realize the goal of achieving this compute intensive tasks of AI algorithms into edge and so on. So if you look at a scenario of a dumb sensor in this figure here, so basically, let's say I'm wearing a smartwatch and the accelerometer here is taking data at all the time. So physical sensors are here in this box. These red dots are representing the data they are gathering. And while I'm taking a step, this green triangle essentially is representing the meaningful events that are occurring to count down my steps in my smartwatch, right? So most of the people nowadays, what they do is to that take all the data throughout the sensors and send them to the cloud for the processing and get back the decisions or whatever outputs they want to give. And in that process, actually, we are consuming a lot of energy for this huge bandwidth that is needed for this data transfer and data movement throughout this cloud, this all these CPS devices that we are actually having around us. And the smartest thing will be to make this meaningful event count itself inside the or near the sensor itself, and then you actually send the meaningful data to the cloud for further processing. And while deriving this meaningful event, that these are essentially some algorithms need to be deployed inside this sensor or near sensor computers. So basically, if you look at these meaningful events, if I'm taking a step and counting step, this is very naive or very typical example of such algorithms. But let's say I'm riding in a bus or car and I want to detect whether I'm riding in a bus or let's say my mini UAV, which is taking some images of, let's say, area of let's say some farmlands or in a smart grid. I need some classification that is need to be run inside this UAV itself. Okay, so that means at that time these meaningful events must be detected inside the sensor or near the sensor. And for these kind of tasks, these algorithms get complicated. And AI essentially actually simplifies those tasks, but they need a lot of computing power to actually fulfill these uh, tasks to be completed, right? So also we have other challenges. So basically, why we want this kind of computations to be computed inside the edge or near the edge is that the three meaningful, let's say, we call them driving factors that are necessary to actually address the issue of computing in the edge from the cloud. So basically, if you look at the communication factor, so we have a lot of areas in the whole world which are not really constrained. I mean, which are not having very tight communication in infrastructure, right? So we need this kind of AI algorithms to be available for all the people to be deployed near the sensor or near the edge computers, right? So another aspect is privacy. You don't want to send all the data to your cloud because there might be reasons for privacy reasons, because you don't want to actually uh, expose the data, all the data, let's say in healthcare section, in the financial care section, or maybe if you take simple example of, let's say, your Alexa, you don't want your all the voices to be sent to your cloud, rather depending on some key features or keywords you want to send. So due to privacy reasons, also you want to deploy these kind of algorithms or this kind of computation inside the edge. And also latency is very, very important, because for the interactive applications like autonomous cars, you want to take decisions at real time. You don't have the time to actually send all the data or video or image that needs to be analyzed inside the cloud and then get back the decision or the results. So essentially, you want to evaluate all the things, all the decisions inside the edge itself. So communication, privacy, and latency will drive you to bring the computations from the cloud to edge. So essentially, a few years back, everything started with a vision shared by many academics, people, and industry people, that we are going to have, we are going to actually deploy all the computations, all the AI computations throughout the entire compute spectrum that we have, from the edge to the cloud. So from the cloud, if you see, we have large iron, we do not have large constraints to actually build or implement those algorithms, that we have enough resources to your embedded systems, like where you need high performance, but you need also higher energy efficiency also, and towards the near sensors, where you need ultra low power of computation of these kind of algorithms. So we are talking about this processing, we are talking about these computations, but how we can quantify these kind of computations, and why we are telling that, well, these kind of computations are very heavy to implement inside the edge, rather compared to your clouds, right? So if you look at these AI workloads, of course we will get into details, but let's look at the scenario. We are actually dealing with how much operations this kind of workloads are having, or these kind of workloads are need this kind of workloads need to be implemented. We need to recount, or we need to take into account these kind of workloads inside the computing devices we are employing. So if we look at the x-axis of this graph, we have these operations in terms of giga operations. And even if you go towards the zero point of this graph, even if you go towards near zero, then also you are operating in terms of giga operations. Okay, you are not scaling down very, very rapidly towards, let's say, few hundred or thousand operations, right? So you are still in the giga operations per range. And if you look at the accuracy, so top accuracy performing AI algorithms will have, of course, orders of magnitude of giga operations that you can see inside the top performing AI algorithms, like let's say Inception V4 and VGG 16, VGG 19. But if you go towards the less accurate or highly optimized for your near sensor processors, these algorithms like Bin and GoogleNet and your ResNet, so these kind of algorithms, or even AlexNet also you can think of. Even if you go towards this lessly accurate or highly optimized algorithms for your near sensor computers, even then also you are performing in gigaops, right? Still you have giga operations per second. So that means we have high computational intensity, right? But this is a really good news for the digital architect or computer architect. So digital designers essentially they look for computational intensity, because they want to actually parallelize those intensive tasks to get rid of the compute bottleneck that can be opposed or that can be posed by these algorithms. So high computational intensivity is one factor. Massive parallelism can be available in these algorithms. That is another good news. And another good news also is that are highly dominated inside this kind of algorithms. Okay? So, and another, of course, this is not the least factor, that is low precision is also highly tolerant for this kind of algorithms. So arithmetic tolerance is also there for low precision arithmetic for this kind of algorithms. So of course you lose some accuracy, but they are a bit tolerant up to a certain level of precision. So that means these essentially are all green ticks for a digital designer, that you can have well-defined, very well-defined MAC operations inside your system. You can have massive parallelism. We exploit this highly computational operations that are present inside those algorithms, and they are also low sensitive to low precision arithmetic. So that means uh, there are possibility to employ very efficiently these algorithms to your edge computers or near sensor computers in short. Now, if you look at the computing need, that means in terms of power, if you think of that how much power we need essentially to actually compute these kind of algorithms, there is a journal called this from Jack Stewart. In this journal, actually, if you look, they quoted some numbers for the computing power this kind of automatic or autonomous car needs. That this kind of autonomous car have employed with several cameras, radar generators, and these essentially generate huge amount of data in very few seconds. So if you take about 30 seconds, they generate at around 6 gigabits of data every 30 seconds. So that means you have already huge data. So this is a big data scenario, but how much power to actually compute or evaluate or analyze this kind of data is also huge. That means you have around 2,500 watts for this kind of prototype that also is employed in autonomous cars. And this kind of power, to actually handle this kind of power, also you need some aspects where you need to employ some cooling mechanisms, some mechanisms to actually tolerate the failures. So these kind of bottlenecks are there, but well, we have the green ticks from the last slide to essentially deploy very efficiently this kind of algorithms. So we will see how and where this kind of efficiency can be generated, and this power, this amount of power can be minimized. So if you to take a look into the today's microcontrollers or processors we are having, we get this kind of curve. So this scatter plot says in the x-axis we have the performance of this kind of processors, and in y-axis in this plot we have energy power operations, that is picojoule. So if you look at this scatter plot, we have high efficiency in energy, but they are very low performance MCUs on the bottom left corner of this graph. And again, we have high performance MCUs or microcontroller units, and they are also less performant, and that means less performance in terms of energy or energy efficiency, if you tell precisely. So we have this trade-off between this performance and energy efficiency, but interestingly, we want to be here essentially. Okay. So what does that mean? That means we want to have 1 picojoule per operation, and that will effectively give you 1 teraops per watt. Okay. So if you can achieve this kind of energy efficiency throughout your design decisions, throughout your through let's say some compiler optimizations, some hardware optimizations, some model optimizations, also some feature optimizations. If you can achieve this kind of energy efficiency, 1 picojoule per operation, then what it effectively means that that AI algorithm, which is inception v4, we have seen the top performant in terms of accuracy, top performant AI algorithm that can be performed at 1 frame per second in 10 milliwatt only. Okay, so our target is this one, and we want to perform inception v4 at 1 frames per second in 10 milliwatt. If we can achieve this, what will happen? That means you can have uh, human vision compatibility or human vision compatible algorithm that can be employed in your smartwatch. Okay, so that is where we want to go. But how that we will see throughout this course, and that is the goal of our tutorial. And essentially, if you would like to go towards also, let's say, 100 times of more energy efficiency in terms of performance, that also you can achieve theoretically. That also we will see, and also how we can realize this theoretical bound to your practical bound. That also is, well, that's very kind of interesting to see what kind of optimizations can be. But before that, we would like to see the trend. Okay, so if you see the trend throughout the year of current scenario, we have a large boost of papers in machine learning, in deep neural networks. So over the years, the numbers are increasing, and every day you can have hundreds of papers available throughout your journals, conference papers. But what does that mean is that the aspects which want to cover is well recognized, well established. That means we have very large area to cover yet. Okay, so that shows essential. And which kind of area we want to cover is the artificial intelligence, of course, in a broad point of view. And if you shorten down your target to machine learning and shorten down your target to deep learning also, you can see that the numbers are increasing in deep learning papers. Okay. Well, so there are multiple aspects why we want to actually pinpoint to deep learning. Of course, these kind of algorithms have very less human intervention to be given, and it can automatically extract feature and all. So those kind of details you can look into the several journals or several books, but the ultimate thing is that we are going towards, or we are moving towards, the era of deep neural networks or deep learning, where artificial intelligence will actually is going to centralize. So with this academia point of view, if we look into the industry point of view, you can see that number of startups are also increasing, which produces the AI chips essentially. So along with Google, Intel, Microsoft, all these big giants, we have very large number of startups are coming in, and that you can also have a look into several journals, several blogs also. And what does that mean is that, again, in terms of research, we have seen the potential. In terms of products, also we have the potential for a big market which is coming. So the goal of this session, this two sessions essentially, is to actually talk about the several trends. But first, we'd like to focus how to evaluate several approaches of deep neural networks, essentially the particular focus of AI algorithms we are talking about. Of course, there are many things to cover here, but the key questions which will be addressed for modern state-of-the-art AI algorithms for DNNs, that we will talk about inside this session. And also we'll discuss about various key metrics which will be used to evaluate these kind of models, these kind of architectures, which kind of models you want to use for your application, why you will be using them, and why your AI on edge will satisfy the targets we have already mentioned, and also how we can achieve this. And of course, in this process, we will talk about several challenges towards achieving these metrics, because there are a lot of challenges to achieve each metrics that we'll see eventually go through as we go along with this course. And also some trade-offs will be there in the different metrics that also we'll talk about. And mainly we will talk about inference more than training, but of course you can actually take all the takeaways of this and apply the same into training. So basically, there will be few changes, there will be few tweaks, but mainly you want to deploy the inferences inside your edge devices. Okay, so mostly we are focusing on inference. That's why. And of course, these concepts which we will be talking about that can be easily applied to training as we have mentioned. Okay. So and why inference and why training, that also you will see in upcoming slides. And first of all, I'd like to, of course, you might be also attending several sessions. You might be referring to several books, several papers. You will be seeing several terminologies, right, for a simple same thing. And here I'd like to use a simple structure of terminology, hierarchy of terminology that we'll be first defining and then we'll be using throughout the session. So that way you will be you'll not be confused about the matrices. And also the key metrics which we'll talk about will give you the design objectives for this kind of models. So we are talking about models and we are talking about architectures. So essentially models are essentially for the architecture of the deep neural networks, and architecture is essentially the hardware architecture mostly we will be referring to. And also, of course, for the design considerations, what kind of targets you will be targeting for implementing or deploying your models or neural network models, that are wide range of choices are there. The spectrum starts from your CPUs, GPUs, and specialized domain-specific ASICs to your other highly sophisticated and highly optimized platform for deep neural networks itself, and also some hardware software co-design which will give you the essence of efficient implementation of this or deployment of these algorithms into your edge devices. And also I'll at last mention some of the tools that you can be using or you can refer to evaluate this performance of these models and performance of these processors. Okay. Well, so with this, we will move towards the basics of neural networks. So this is very important to know the basics, but the basics we will not cover into much details because that will take time. So in the essence of time, I will overlook or I will give you very high level idea of this kind of neural networks. So if you see neural networks, what are neural networks? Are essentially stacked layers of your input layers to your output features. Okay. So you have many stacked layers, and throughout these layers, you want to achieve or you want to evaluate multiple features. Okay. So with each layer, if you go from left to right, you would like to evaluate low level features to high level features. So here we are giving you a very simple example of an image that are being evaluated to your high level feature at the end. Okay, and at the end you are actually classifying this image as a Volvo this model. But the main idea is that with each layer you want to you are stacking those layers, and with each layer you want to extract features from low level to high level as you go along the left from the right of the stack. So now for the color combinations, for the ease of understanding throughout the lecture, I'll be using blue as the input feature map or input activations. So basically, each stacked layer will be having some activations or some points that we'll call activations, and those are, if they are used as inputs, though those are essentially colored as blue, and if they are used as output, that means output feature map, or let's say the partial sum that will be calculating on the input features or input feature map. So essentially, input feature map is essentially the matrix of these activations, input activations, and you will get output activations from this input activation. And output activations will be, or output partial sum will be referred as the color red here, and the green color will be representing the weights, which is the main target of learning phase. Okay, so as we have mentioned that each neural networks or each neural network architecture has two phases. One is learning phase and another is inference. And in the learning phase, we are trying to evaluate, or we are trying to get the values of these weights, which are referred to as green color inside this slide, and that will be using the same color combinations for this slides. So again, just to be concise, we have input features or input feature map colored as blue, output features colored as red, and then we have green weights or filter values that are green colors. Okay. Okay. So next, so basically, what are going on inside these input features and output features? So in the previous slide, you have seen that multiple layers are stacked in to extract high level features at the end. Okay. And we are calling these deep neural networks because the depth of the neural networks will be confirmed or will be determined by the depth of the layers. Okay. So the number of layers we are employing will confirm the depth of this DNN or deep neural network. So essentially, in each layer, you are computing this output feature map from this input feature map. And how you are computing? Well, you have this input layer with different activations. So you have, let's say, x1, x2, x3 as your input activation. So essentially, if you take an image, these are essentially the pixel values. And for the hidden layers that are the next, so let's say first a layer is essentially one hidden layer where you are getting these output features from these input features, y1, y2, y3, y4, and these are essentially the weighted sum of the input features. Okay, so very simple. So we have this y1 as the weighted sum of x1, x2, x3, y2 also weighted sum of x1, x2, x3, and y4 as well. But the main important thing here is that these weights will be learned in the learning phase, and that you will use, or that will be used inside your inferences. Okay, to infer or to classify or to extract the feature of your input. So in this lecture, we'll be mostly referring to images, but not necessarily they can be image, they can be anything. Okay, so they can be sound signal, they can be your PME signal that is coming inside, that can be a signal from, let's say, acoustic, that can be any analog input that can be that is digitized, so that any input you can take into account in your input features, and then you can extract several features throughout these several hidden layers, and at the end you will get some probability distribution for your different features you are classifying. So basically here inside, as you can see that we are passing through these linear activations, that means linear partial sums through nonlinear activations, because we want some these weights to be actually dependent on the several layers of these hidden layers. Okay, so if this is a single linear combination, so at the end, even if you have multiple hidden layers, that will be considered as a single hidden layer, because all the linear functions can be coincided to a single hidden layer. So there you don't have the flexibility of going into deep feature extraction. So only one feature you can extract. But if you want to have multiple feature extraction, then you want to have this non-linearized activation function applied on these partial sums. Okay. So there are several nonlinear activation functions that are being used, sigmoid, ReLU, and you can loop those. There are a lot of references for these kind of functions. But the main key take point is that most of these operations inside this entire network is multiply and accumulate, as I mentioned before. So if you look at a very state-of-the-art neural network architecture, greater than 90% of the computations are known only. Okay, and that gives you very good optimization area that opens a completely new domain of optimization for you for this kind of algorithms, for this kind of state-of-the-art AI algorithms. So with this key point, just to summarize, we have input activations, we have output activations, which are partial sum of these input activations or input features, and they are essentially computed through a nonlinear activation function, and multiple hidden layers will be there for extracting multiple features, okay, from low level feature to high level feature of your data. So if you look into what kind of popular layers are there, we have feed forward. That means the output layers will be fed by the input layers only. Okay, we have this kind of network. We have another layer called feedback layer, where output can be output layers or output activations can be fed with feedback itself. Okay, so that means output is essentially driving the outputs also. So okay, so this kind of layers are also there. We have fully connected layer. We have sparsely connected layer. Fully connected layer is essentially all the input activations are driving all the output activations, and sparsely connected is essentially not all the input activations will be driving all the output activations. Okay. So if you look at the fully connected layers, we have feed forward and fully connected, and mostly they are used in multi-layer perceptrons. And if you look at convolution layers, which are essentially feed forward layer type, but they are sparsely connected with weight sharing, of course. That means multiple weight can be shared for multiple activations. And they are essentially used in convolution neural networks that are CNNs, widely known as CNNs. And going forward, we will take CNN as driving example, but that same technique or same methodology can be applied to several other layers as well. And these are typically used for images, convolution layers or CNNs. And there are recurrent layers which uses this feedback type of layer. And this kind of recurrent neural networks are used in sequential data mostly, which are like speech, sound. So this kind of signals are evaluated through this RNNs mostly. Okay. And we have attention layers. These kind of attentions are mostly associated with matrix multiplication combined with feed forward and fully connected network. And those are used in transformers. And here is the reference for that you can refer to. These kind of networks are very, very state of the art and recent ones. And as I mentioned that going forward, we will take into details in the CNN types of network, and that can be applicable to the idea can be applicable to all the networks that you are seeing here. Okay, so going forward, what are the convolution networks or convolution layers? So you have a filter which will be applied to your input feature map, and then you will get the output feature map. And the dimension of these filters are essentially will be mentioning as R into S, and that will convolve through this input feature. Okay, so the size of this input feature or dimension will be h by w, height and width of the filters will be defined as R and S, and these conventions will be used throughout the slides. So with this, we have how we were getting this convolution. You are doing element-wise multiplication throughout these filters, through these filters on this input feature map. And with the element-wise multiplication, you are actually getting throughout, you are convolving, and all the element-wise multiplication, combining them or partial summing them will give you output as an output activation. And if you slide through the input feature map with this filter, you will get all the activations. Many activations you can actually give output as your output feature map. So your output feature map will have essentially E by F dimension, which is the height and width of the output feature map. So these CNNs or these filters will work as convolving through or sliding through the input feature map, and all the partial sums will give you the output activations. So here we are seeing now what is called we call is the 2D convolution, but essentially in practice, what kind of CNNs are applied for images? They are multidimensional convolution. Okay, so what kind of dimensions we have, that also we will discuss, and essentially at the end we will see that what kind of features that can be extracted through this multidimensional convolution or multidimensional, let's say, multiplication or accumulation, which is coming through this partial sum and this convolution, and give you very, very good optimization techniques. Okay. So first dimension we are adding is that many input channels might be there, which will be applied through many channels of input feature map. So here the width of this channels is C essentially, and all the partial sums from all the channels will give you one activation in the output feature. Okay, so this is just one dimension we have added, and the challenge is not only one dimension. Challenge is here that many dimensions are added, and that blows up your entire model or entire network architecture and the deployment also. Okay, so this is very, very interesting to see from the core point of view how they are actually getting deployed inside your hardware and how you can optimize that. So this is essentially the first kind of higher dimension we are adding as the number of filters. So as many as filters you can have, that many actually output channels you can create. So essentially this number of input filters can be varied in terms of hundreds of numbers. So for the example, we have AICTE where we have 96 to 384 number of filters, input filters that are being used. So in this kind of CNNs, we have so R and S is the height and width of these filters, C is the channel length, and the number of filters is capital M here. And throughout this different number of filters, we are creating different channels in the output feature. Okay. So that means m number of output channels will be created throughout this m number of filters. And also you are adding batches. Okay, so not only the channels, not only the number of filters, also the number of batches. So you would like to have many number of images to be evaluated at the same time, and here each batch is essentially each image is each element in the batch. So how many batches are here? We have n number of batches, capital N number of batches, and throughout these batches we are creating that many output feature maps. Okay, so we have m number of channels in the output feature maps that were coming from the m number of input filters, but also we have n number of output feature maps that are being created. That means in batch you are creating output feature maps, that n number of feature maps that you are creating throughout this n number of input feature map in the batch. So in summary, we have H as the height of input feature map, W is the width of input feature map, C is the number of 2D input feature map or filter channels. That means the number of channels you are using inside the filter. So all these numbers will essentially be using inside the optimization, or where we will talk about how much optimization you can achieve. So HWC is the height, width, and number of the channels inside your filter, and the RS is the height, width of your filter, and M is the number of 2D input feature maps, that is the number of filters also, and E is the height, E and F is the height and width of the output feature map, and N is the output number of output feature maps that you are creating. So total this many matrices will be varying throughout the layer. Okay? It's about several layers. So that there the complexity lies. So these numbers, HWC, RS, MEFN, all these numbers will vary throughout the layers. And that we'll see if you take an example of a simple mobile net V3, which has a large number of convolution layers and the different configurations for different layers. You can see that filter size RNS is different for different layers. Number of filters also different for different layers. Number of channels also different for different layers. Okay. So you have large variety in terms of different parameters in this, or different dimensions in the filters, in the channels. Okay. And if you look into the several DNNs, so here we have LANet, AlexNet, VGG, GoogleNet. So these are different modules or different DNN architectures. So as I mentioned that we will be using models for neural architectures and architecture for hardware architecture. So models, if you see different models, with the increased accuracy, so essentially you are decreasing error as you go towards right. So with the increase of accuracy, you are increasing the number of convolution layers you are having. So from 2 in LANet, 5 in AlexNet, 16 in VGG. So the number you are increasing in the in terms of convolution layers. Weights are increasing as well, from K to mega bytes of weights you are actually introducing. You are increasing the number of max essentially, which is the number of giga operations that we talked about. And the fully connected layers also are increasing, and in the fully connected layers we have also weights and max are increasing. Okay. So these different numbers in different models, different numbers in the different layers itself in the same model, different dimensions in the filters, all these poses essentially the challenge of implementing this kind of state-of-the-art AI algorithms into your edge devices, or even if you take about cloud, these highly efficient or high accurate uh, network models also poses very significant challenge of implementation. So we need to look into some matrices to actually see that how we can evaluate these models and these architectures. Again, models referring to the neural network architectures and architectures referring to the hardware architecture. So how we can actually evaluate the performance of these models and the architectures very concisely and effectively, so that in the same place we have the eagle eye point of view of the entire world. So until or unless you do that, you are essentially in the dark. Okay. So what are the key matrices which we are talking about to evaluate different kind of systems and different kind of algorithms or different kind of network architectures? So we have accuracy, of course. That's why we are here. We are doing DNNs because of the accuracy, and the accuracy varies from model to model. So the accuracy you are getting for different data set in MNIST will be different for your image. Okay, so quality of results matter at the first itself. So if you don't comply with the accuracy, then you're gone. And the next, you want to consider the throughput. That means how much volume of data you can perform or you can give result to for a particular time. And this is very important for your data centers, and this is for your important for your real-time performance embedded systems also. Let's say you are taking video at 30 frames per second, and your throughput for your algorithms or network models which you are applying on this video will be compliant for these 30 frames per second. Otherwise, it will not work. And latency is also very important for interactive applications like autonomous navigation. You want to take decisions at the same time or real time as you are capturing the data. So here the latency and throughput are having this kind of notation of like the batch processing and individual processing kind of concept. So essentially, throughput is kind of laundering your entire week's dirty laundry. Okay, so you have socks your accumulated throughout your week, and you are processing them or you are cleaning them at the same time. So the processing time for each sock will be very minimal, and you are increasing throughput. But if you want to have your sock, a particular one sock is clean in a particular time, that means you have to do the laundry at the same time without just accumulating all the socks, right? So the application matters. Okay, so if it is real time systems, you need to have lower latency, okay, and high throughput as well for your particular application. So that's why this the concept of throughput and latency is very important to understand and to deploy your AI algorithm into your devices. Energy and power is coming in the next, and which is it is lying in the middle, but it has the most implications of implementation. So if you are, let's say, working with embedded devices which has limited battery capacity, you cannot have higher energy consumption. Okay, so essentially energy is power into time. That means you want to have higher throughput as well, and also power consumptions must be lower. And if you are operating in the data centers, there is a power ceiling that you need to comply with. Otherwise, you need to have to take care of the cooling system. So cooling cost is very high, and for these data centers, if you can look into that, they spend billions of dollars to actually implement these kind of cooling systems for a particular data center. Hardware cost is essentially very important for evaluating your devices, because of course the lower cost hardware will not give you the accuracy, the performance which you are trying to achieve compared to your high cost devices. So So the cost of the hardware is also a key factor. And the flexibility, well, you must have flexibility, because this kind of domain is very uh, you can call highly flowing. Okay, so every day some new events are coming, every year some new perspective are evolving, and you need to comply with your hardware, or let's say with your deployment strategy, comply with all the recent advancement that is taken to or taking place inside this domain. So that means you need to have flexibility in terms of supporting several algorithms, several models, as well as their updates, right? And also scalability is highly important at the end, uh, because you have, let's say, a limited amount of resource, and if you are given a scaled up amount of resource, you must comply with scaled up factor of performance, scaled up factor of energy consumption, scaled up factor of latency. That means improvement, of course, that you might provide. Otherwise, the deployment will not work. So that means the scalability must be taken into account. So all these key metrics will essentially define how efficiently you can deploy your AI algorithm onto your. Of course, without talking about key design objectives, it will not be very wise to go along, because you need to take into account how to actually you want to optimize, or you want to increase the throughput, let's say, or reduce the latency. Okay. So if you want to reduce the latency, that means you want to reduce the time per MAC operations, right? So MAC operation is the ultimate or key operation in these models, as we have mentioned. That means to reduce the latency, you want to reduce the time per MAC, and the critical path of the hardware can be improved by increasing clock frequency, or reduction in the instruction overhead. Also, if you are working in a programmable hardware, and also you want to avoid unnecessary maths. That means, let's say, some operations are doing with multiply with zero, so those kind of operations you want to avoid, to actually save some cycles. So through this kind of approaches, you want to reduce the throughput, and so the key objective is to increase the throughput and reduce the latency. But of course, there is a limit for reducing the time for MAC. There is a limit for avoiding unnecessary MACs. But in the same time, you would like to increase the number of processing elements. Here, the processing elements means the hardware, or the piece of hardware which is doing the MAC operations. Okay, so essentially, you want to increase the number of processing elements, of course, in the given cost of hardware. Otherwise, you will blow up the cost of the hardware as well. So for a given cost of hardware, you would like to increase the number of processing elements, more number of MACs in parallel you will get, and that will increase the density of the P, or the area cost system. So as I mentioned, that for a given cost, if you can, you want to increase the number of processing elements. That means you want to increase the parallelism that is available inside your architecture. And also, increasing the processing elements will not give you the ultimate performance. That we'll see shortly. But you would like to also increase the P utilization, because without keeping the P's busy, that means you are losing the utilization, or you are losing the parallelism that you wanted to achieve. So that means you want to utilize the P's as much as possible, as many as possible, in numbers that you want to have. And how you can achieve this higher utilization factors? You would like to distribute the workload as many as you can throughout the P's you have. And also you want to balance the workload, because without balancing, some P's will have some extra cycles to wait to complete other Ps. Okay, so that is why you need to balance the workload throughout the Ps to actually essentially get the higher utilization factor out of this entire array of processing elements or entire fleet of processing elements that you have. And also sufficient memory bandwidth, which is the most important thing we'll talk about. And this will actually reduce the idle cycles, but how it is affecting that we'll see. And with this increased throughput and reduced latency, in addition to this, you also have this objective uh, to lower the latency through decreasing the batch size. Okay? So that means, let's say inside your autonomous cars, you want to have batch size of 1. So it will take one image, it will process it, it will give you the result, and you want to have better latency and you want to decrease the latency and you want to decrease the batch size as well. So with this design key objectives, we'll see how these performance are being evaluated essentially. So we talked about that what is the maximum performance that can be achieved, but the key matrices like throughput and how the performance or throughput is being affected, that also you see to effectively deploy these algorithms onto the hardware. So here x-axis is essentially giving you the MAC per data. That means given a piece of data, how many MACs you are calculating. And y-axis is giving you the MAC per cycle. That means the throughput or performance that you are achieving. Okay. So this is a roofline model that you can look into this reference that I have referred here. This is a fine example of a paper that is setting up a framework that is called IICTE, and this framework will give you that what kind of maximum performance that you can get from a given model, from a given architecture, for different constant environments. Okay, so this is very interesting graph to look at. So if you see in the x-axis, in the y-axis, we have this step 1. So that means if this is a roofline model where you can get this maximum workload parallelism that is coming from the model itself. Okay, so that means this model is saying that this much parallelism it has already. Okay, so if you want, you can achieve this much maximum performance throughout your strategy, right? And next, in the step 2, you have this maximum data flow parallelism. That means when you want to implement this this model essentially in real or in practice, how much data flow you are actually getting parallelized. That means how much feature map you are input feature map you are getting parallelized, how much filters you can parallelize. So throughout this implementational aspects, you will get some reduced performance through this step 2. So that means that will that you will get from the maximum data flow. And next peak performance you will get from the number of Ps, which are the theoretical peak performance that you are having already inside your hardware. Let's say your hardware is having 1,000 number of Ps. That means though your model has this kind of parallelism, which is mentioned in step 1, though you can achieve this data flow parallelism in step 2, then also you are limited to this number of parallelism in terms of Ps essentially, which we will implement that into hardware. So theoretical peak performance of this hardware is the number of Ps that is had. Okay. So so essentially this kind of performance is not only bounded by this P number of Ps. Here you can see a slope as well. So that is essentially the memory bandwidth or memory access slope. So that is also very, very important to take into account, because that you will see in the next slide. So when in the data you will be getting to evaluate through these DNA models, you will be bounded by two kind of aspects. One is compute bounded and one is bandwidth bounded. Okay. So compute bounded are essentially where the computations are fully at your disposal. That means you are not essentially compliant to your memory. Okay, so those are mostly compute bounded. That means mostly convolution layers are this kind of regime lying into the compute bounded, where you can get maximum theoretical peak performance of number of P's that is available inside the hardware. And throughout the bandwidth bounded, where you have some dependency on your memory, then you can have this bandwidth boundary, but that means these P's which you are having inside your hardware cannot be fed all the time throughout this memory. So that means there will have some bandwidth issues that you need to take into account, and this slope is essentially the bandwidth of these. And mostly the fully connected layers are lying in this kind of region. So this root line model is giving you the theoretical peak performance of your compute bounded and bandwidth bounded compute parts of your network models. Okay, and there are several other factors as well. So if you look into their finite P array size, the maximum number of storage capacity that you can have. So step 5 is essentially important. That I'll not go through all the steps here. You can have a look into this paper, and this is very good to read as well. And in step 5, you will see that number of active P's. Okay, so as I mentioned, that you have this number of this high number of P's inside your, let's say, hardware, but how many active P's are there? That is very important. And also, how many active P's are essentially have the storage capacity? Not all the P's have the storage capacity. Not all the active P's have the storage capacity. So as you can see, we started with step 1, the maximum workload parallelism that is available inside your model, but with different steps, we are essentially decreasing the peak performance, which we can achieve in practice. And at the end, in step 5, we ended up with active P's with storage capacity. And not only that, we in practice, in real, we have at least at the step 7 level, where you have lower performance due to the insufficient instantaneous bandwidth. So essentially, instantaneous bandwidth is your bandwidth is fluctuating throughout the layers. Okay, you do not have a very continuous variation of these bandwidths. So it will fluctuate throughout the layers, throughout different computational layers. And at the same time, if you take into account all the fluctuations, you will end up with this kind of lower performance that you can imagine, or you have modeled throughout your DNA model that is the theoretical model. Okay. So that is bounded by the bandwidth of memory as well. Now, with this, we will see that, of course, throughput is the key metrics that we have seen, and there are multiple, let's say, bottlenecks that you can actually will be stumbling block to achieve your maximum peak performance or maximum throughput. Well, so now the key design objective is to reduce the latency, as we have mentioned. So the latency can be reduced through several, let's say, reducing the cost of the MAC units, and also the energy is the key feature, as you are operating in different regime of different MACs. Okay, so here this list is giving you different, let's say, multiply and add with different precisions. So 8-bit, 16-bit, 32-bit. So different add, different multiply, different operations with different precisions that you are seeing here, and as well as with the memory operations. And this is the most important part of this session, is that the memory operations take the most energy consumption, or the energy cost of the memory operations are the highest. So even if you scale down the performance of the MACs, then also you might end up in achieving or might end up of getting higher energy consumption. Okay? So that means you are not essentially looking into the memory operations. So the key objective is to reduce the energy or power consumption. And to reduce the energy and power consumption, data movement you need to reduce. And data movement is the dominating factor of energy consumption inside your model. So as you can see here, SRAM is the on-chip memory. 8 KB on-chip memory is giving you the 5 kilojoule, 5 picojoule of energy per operation or per, let's say, data movement from your memory to your PE. Okay, so this is the on-chip memory transfer. And if you look into the off-chip memory transfer, which is from the DRAM, we have orders of magnitude of greater energy consumption in off-chip memory transfer. So that means you want to avoid unnecessary max as well, but the main thing is that you are limited by the power distribution through these memory operations, and you want to reduce this memory operations as much as possible. And how you can reduce that? You can reduce that through exploiting data reuse. That means you want to reuse the data which you are being generated, not storing into the memory again or taking from the memory. Okay, so you want to reduce the memory transfers through data reuse, that you will see also in subsequent slides. So as a few other key objectives, as I have mentioned earlier, the flexibility, we need to reduce the flexibility, the overhead of support, supporting all the other network models you want to deploy into your hardware. That means you want to reduce the overhead of supporting flexibility. That means you don't want to have higher added hardware to actually take advantage of other network models that are available. And you also want to maintain efficiency across the wide range of DNA models, not only to deploy them, but also they must be deployed efficiently. That means part of the available data reusage options that are available in several networks, that also you need to take into account. You need to actually model the storage and compute so that the storage and compute are kind of balanced to give you the peak performance, and you don't have that high slope that we have seen in the last few slides. And also different precisions across few different layers. So this is highly flexible. So the weights, activations, and partial sums that we'll be calculating will be can we actually have different precisions through different networks so that we can take advantage of that different precision power consumption hierarchy, and different degrees of sparsity. That means you want to reduce the number of connections, number of ways that to be used in the max, or you want to have different layers of max. That means you want to have different activation functions that are available throughout different layers to be actually employed efficiently inside your router. And scalability, that means if you are thrown to you as many as number of Ps, as many number of memory, are you able to scale up your throughput, scale down your latency, scale down your energy consumption? So that means if you are not, that means your approach is not correct. So all these key features you need to take into account. So not only the energy, not only the accuracy, not only the throughput. So all these things need to be taken care of to trade off. So going into deeper, accuracy varies from different let's say models for different data sets. So a model which will give you higher accuracy in image data set will give you lesser accuracy in ImageNet data set. So that means you cannot just compare apples to oranges. Okay, so you need to have apples to apples comparison. So with accuracy, you need to have perfect comparison with the perfect data set and which you are using throughout the. So you just cannot build a model or cannot give architecture that you are showing that through MNIST data set it is giving higher accuracy, but you are not reporting the accuracy for ImageNet, but you are actually claiming that it is giving that much of accuracy. So that is what I'm trying to say. And throughput also, in terms of number of P's of utilization, you don't actually give the number of P's only. Okay, so you give how much utilization that can be achieved throughout this architectural, so that the active P's you are utilizing, that is the ultimate thing you want to report. Running time as well, latency, batch size, how many batch size you can evaluate, energy as well for the. So most of the academic papers, if you see, they actually report the power consumption of max only, and they claim that they have very high power consumption. But you want to give the entire power consumption of off-chip memory access, chip memory access. Otherwise, it is not exactly the whole thing. So as we have seen already, that the memory accesses through DRAM is many orders greater than the on-chip memory access. You must give the figures of off-chip memory access as well. Otherwise, you are not giving the entire picture. That means you don't have the entire picture for this kind of models or for this kind of architectures. Hardware cost, you need to have the cost as well to be defined in terms of P's, chip area, the process technology you are using. Otherwise, there is no point. And the flexibility as well, how many range of DNN models you are supporting and tasks, that is important as well. So as you can see, to comply with all these factors, there are large number of design choices that can be evaluated, and then only. So as example, for the scalability, you need to define the number of ranges, DNN models, and for, let's say, a fair evaluation or trade-offs, without the given accuracy for a different for a given data set, you would like to give the accuracy for different data sets. You need to give the performance for on-chip memory access, off-chip memory access, the total power consumption. So everything you need to actually give into account. Otherwise, or whether these results are measured in simulation or actual in the hardware, or the test data, which test data you are actually testing. So all these kind of factors will give you the entire picture. Otherwise, if you are starting with some so you have very higher utilization factor with the hardware, but this is not giving very high accuracy throughout the different data sets. That means this, even if it has very less power consumption, high energy efficiency, this is of no use. Okay? Well, so for the CPUs and GPUs, we are targeting first that, as I mentioned before, but for targeting these kind of targets, you need to have, as I mentioned, that max are the dominating performance or dominating performance computations that must be taken into account. Most of these state-of-the-art GPUs and CPUs have matrix multiplication libraries as Xeon processors for deployed in data centers, servers, NVIDIA, Tesla, AMD, Radeon, and all the GPUs are coming, all the CPUs are coming with matrix multiplication libraries in specific. Okay, so you would like to use those matrix multiplication libraries to achieve better performance, and how you are going to achieve that we'll also see in this subsequent. So first of all, take an example for fully connected layer, right? So for the fully connected layer, we had this input feature map of the same size as the filters. So that means here all the input activations sorry, all the output activations are essentially dependent on all the input feature maps. So essentially the filter map, filter size and the input feature map size is same. And so HWC, C is the channel width, the M is the number of filters you are using, and N is the number of batches you are using. So now you are outputting this N number of output feature maps with this dimension, okay, with each feature map having M channels here. So now how we can convert this into matrix multiplication? This is very simple, very straightforward. So the M will be the size, height of your resultant filter, and C into W into H, which is the dimension of the number of filter elements, will be your column size here in the input filter matrix. So here M into CHW is your filter size in your matrix multiplication, and for your input feature map you have the size of CHW and N as the column size. So basically you are multiplying M into CHW and CHW into M matrices, and at the end you will be getting M cross N output feature map. So this is very simple. As you can see, this through matrix multiplication you can use, and heavily you can actually convert these computations into a matrix multiplication library, and these are used in recurrent layers, attention layers. Mostly these fully connected layers are used. So this is very simple and straightforward for the fully connected layers. But for the convolutions layers, what are to be done is that filters are not exactly of the same size as the input feature maps. So you need to have some way of scaling things up, right? So essentially filter is convoluting through the input feature map and giving you the output feature map. So essentially, if you are applying this filter onto the, let's say, first quadrant of this input feature map and getting the first output feature map value, you can convert this into you can convert the filter into a 1D vector here, as you have seen here, and the input feature maps to a Topli's matrix conversion. So 3 cross 3 map input feature map will be converted into a 4 cross 4 input feature map, and then you can actually use the matrix multiplication library to get the output feature map of size 1 cross 4. So essentially, what you are doing here, you are just converting this, or you are doing a Topli's conversion in the input feature map for using or efficiently using the matrix multiplication library that are already there for your device. So here, as you have seen in the course of this transformation, you are adding some extra values and adding some extra operations, but nonetheless, your things are getting easier. So with this simple example, we have pointed out the libraries that are available for CPUs, OpenBLAS, and Intel MKL. This is very you can say a popular library for all the Intel processors coming nowadays. And for the GPUs, CUDA are the most popular. CUBLAS is also another library that you can use for. And also you have to notice that the compiler is doing all the thing of optimizing your matrix multiplication. So basically what kind of conversion will be taking place, and how this map input, how much of size this input feature map will be converted to how much size of output feature map. So those kind of conversions will be taken care by the compiler itself, and your compiler must be compliant with this kind of taking this kind of features as. So with this this tiling matrix multiplication that we'll see in the next day, we'll keep 5 minutes for today's question and answer, and also we'll continue more with the next classes, next session. So with this, I'd like to conclude the session here, and I'd like to welcome all the questions. Thank you.
Thank you, sir. There is one query. Can I read?
Yes, sure.
Okay. Can you suggest some good coding online source for deep learning and also for deep reinforcement learning?
Yes, exactly. The coding sources, and also not only the coding sources, I'll mention some tools as well. So you can use very efficiently these tools to evaluate the performance of these models. At the end of the next day's session, I'll actually refer to all these resources that I have already taken into account, and you will have very good resources to actually go through later on. So I'll give all these resources at the end of the next session. So any more questions?
Another question. Usually in power system area, we deal with 1D signals. Which DNNs are suitable for prediction and classification of 1D signals?
Yes, this is very good question from the power systems point of view. So essentially, if you are using a single dimensional signal, you can actually go to your I can say the classical machine learning techniques. Okay, so let's say simple regression, simple decision trees. So those kind of things will be much cheaper, much easier to implement, and much effective as well. And if you are dealing with multidimensional this kind of data, let's say currently I'm also working with synchrophasor data. So PMU from the PMU signals that we are actually detecting some events and things like that, and there we are using classical machine learning algorithms. Ensemble learning also we are using some for some time series analysis, and also some for some classification techniques that we are using. But at the end, if you are having say multidimensional data, then you can go for deep neural networks. Otherwise, this will be very costly for your implementation. So DNN inferences are very costly, as you will see in the next lecture as well. So I have chosen this DNN for this lecture is because of the complexity only. Okay, so DNN models are very complex to implement. That is why it is kind of very hot research topic nowadays also. But if you are using a simple single dimensional data, you can go back to your classical machine learning techniques and you can use this. And that will be very cheap as well. And also if you are dealing with images, let's say for our smart grid management system, we are also working on one part as the image analysis of the whole smart grid to detect some let's say some faults in the motors and all. So there the UAV images are mostly analyzed through DNNs. So of course, if you are dealing with speech signals or sound waves, or let's say images, then RNNs and DNNs are very efficient. And if you are only single dimensional data you are dealing with, you would like to use the classical machine learning techniques. Thank you. Yeah, next question. Yeah.
Can tool like Tableau and Power BI be used for visualization in power system? If yes, how efficient are these tools?
Yes, so these are not very highly customizable. Of course, for analysis and visualization, Tableau is very good. For visualization, mostly Tableau is very good. And if you have very customized, let's say, again, I'll give my practical example of my experience. So we are again dealing with synchroprocessor data, and there we are dealing with a lot of data visualizations. Let's say this voltage variations, frequency variations, this uh, so all these kind of visualizations we are dealing with simple Python library. Okay, we are just dealing. I mean, we are not going to these sophisticated tools. I mean, you don't get the feeling of very customized things. Of course, you can have the full visualization. I mean, lot of options are there. You can explore. But if you want to have your own and very customized to your own preferences, then I will suggest you go for simple MATLAB libraries and Python libraries. That is the best way to actually visualize simple things.
Okay, sir. One more query. Please differentiate the application of CNN and RNNs like LSTM. Please differentiate application of CNN and RNN like LSTM.
Yeah, so as I mentioned that mostly CNNs are used in terms of the images, video processing, image signal. So all the smart cameras nowadays are coming with not only smart cameras, so inside your mobile cameras as well. So all these camera chips are coming with CNN model chips. So mostly CNNs are used for this video and image processing. And I have already mentioned that recurrent neural networks or RNNs are mostly useful for your speech data or sequential data. So mostly whatever data you are getting. So if you consider an image, you have entire pixel at your disposal. So full array of pixel is at your disposal. At that case, only the case of CNN will give you the maximum flexibility. And if your data is sequential in nature, that means you don't get the entire spectrum at the same time. So you want to have some recurrent neural network, and simply RNN will be very efficient in that case. And of course, speech, sound, and those kind of signals are kind of example for efficient processing through RNNs. Yeah.
Sir, is it okay to ask one more query?
Yes, of course. Yes.
How to choose the batch size in? Is there any deciding criteria?
Yes. So essentially, batch size is if you are deploying, let's say, as I mentioned, if you are deploying in, let's say, in autonomous vehicles. Okay. So there you want to have batch size of only or single image you want to actually infer.
Any queries from the participant side? Okay, sir. Thank you. So we'll continue.
Sorry, I'm losing your voice.
Hello, sir.
Yes, I can hear.
On behalf of Power and Energy Group NIT Calicut, I would like to express my sincere gratitude to Professor Satyajit Das for having a session on the topic AI on Edge. I hope the session has given a clear idea about difference between cloud and edge computing, an overview about the approaches for efficient processing of DNN that includes design of DNN processor and DNN model. Once again, thank you so much, sir, for spending your valuable time with us. And I would really like to appreciate your efforts to make the session more informative. Thank you, sir.
Thank you, sir.
Thank you so much.
Thank you, sir.
Yeah. See you tomorrow. Thank you.
Hello, sir. Sir, I will share the tomorrow's link with you.